Hello, my name is Michael Y. Session, and welcome to Lecture 8 of our course on the geologic wonders of the world. Now, in the last lecture, we looked at the Grand Canyon in Arizona. In this lecture, we're going to go around the world to visit a place with lots of big canyons, and lots of big mountains, and frankly, lots of big everything. The Tibetan Plateau, including the Himalayan mountains. When viewed from space, it is likely that there is no more impressive geologic wonder than the Tibetan Plateau. It's 2.5 million square kilometers of land that's approximately 5 kilometers above sea level. It's called the roof of the world. The Tibetan Plateau contains the world's highest mountain range, the Himalayas, sometimes also called the Himalayas. It contains the world's highest mountain, Mount Everest, at over 29,000 feet. It contains a lot of high things. Now, there's actually a lot of different ways to define high or tall or big. As a mountain range, and again, with a mountain range, we're talking about a long chain of mountains that usually form at the collision between two tectonic plates. As far as mountain ranges go, the Andes in South America are by far the longest, more than 7,000 kilometers. The Himalayas are only 2,400 kilometers in comparison. The Andes are currently growing by the subduction of the Nazca Plate, part of the Pacific, that we saw in Lecture 3 on the Galapagos Rift. That subduction occurs beneath the whole extent of the west coast of South America. It's the longest continuous subduction zone in the world, and therefore the longest mountain range. As far as a single mountain on land is concerned, Mount McKinley, or Denali, in Alaska, rises farther from the surrounding valley than any other mountain on land. It's 18,000 feet above the surrounding plains. For Mount Everest, it's only 12,000 to 15,000 feet. Not only is Denali the result of the collision between North America and the Pacific plates, with lots of thrust faults that have lifted up the rock, McKinley is made from a giant mass of hard granite, so it erodes more slowly than other mountains might. But McKinley is also forming from a compressional bend in the strike-slip Denali Fault, much like the San Gabriel Mountains north of Los Angeles, how they are pushed up by a bend along the San Andreas Fault. Only it happens on a much larger scale, and Denali is still going up. And as a single mountain, nothing compares to Mauna Kea on Hawaii, which rises more than 33,000 feet off of the seafloor. Now, most of this mountain is underwater, but if you take, again, the top of the mountain compared to the surrounding lands, Mauna Kea wins the prize. We'll see more of this in Lecture 24. And remember, from the second lecture, the peak of Chimborazo in Ecuador, because it's at the equator, which bulges out compared to the rest of the planet, Chimborazo is the highest point measured from the center of the Earth. But it's impossible for anything to compare with the Tibetan Plateau in terms of just sheer size. For example, look at the number of tall mountains there. There are about 450 mountains in the world that are more than 7 kilometers above sea level. Every single one of them is part of the Tibetan Plateau. The next highest mountain outside of the Tibetan Plateau is Aconcagua in the Andes in South America at 6,962 meters high. The Tibetan Plateau doesn't contain a single mountain range, but many of them. Usually, if you go to a place like the Andes or the Appalachian Mountains, you have a long range, but it drops away on either side. It's not the case for the Tibetan Plateau. There is just mountain range after mountain range after mountain range. If you are actually there and view it, it is just an incredible sight. So many large mountain ranges exist in this part of the world. On the north side, you have the Kunlun Range, the Kilian Range in the northeast, which borders the Gobi Desert. On the east, you have the Hengduan Mountains in the Sichuan province of China. On the west side, you have the Karakoram Range in Pakistan. But most impressive of all, of course, is the Himalayan mountain range, which is at the southern end of the Tibetan Plateau and separates it from the Indian subcontinent. The Tibetan Plateau contains also an enormous amount of water, mostly in frozen form. The Himalayas alone have about 15,000 glaciers that carry as much as 12,000 cubic kilometers of ice down out of the mountains. In fact, the rivers that form from the runoff from these glaciers feed 3 billion people. I mean, almost half the people in the world get their water that starts up here in the Tibetan Plateau. And you can see the major rivers that come off of here. The Indus River Valley coming down on the west side. The Ganges and Brahmaputra rivers coming out emptying through Bangladesh. The Mekong River that flows out through Southeast Asia. And then the Yangtze and Yellow rivers in China. Just an incredibly important source of water for a major part of the world. There's an interesting question there. Why is all this water here? Why does the Tibetan Plateau act as a source of so much of the world's water? Well, it's because it's a huge barrier to the monsoon air patterns. What happens in India? India has a monsoon-type climate, which means for part of the year, massive, moist, warm airflow comes off of the Indian Ocean and heads north up across the Indian subcontinent. As it does, the rain falls and drops out. And then as it begins to hit the Himalayas, that air has nowhere to go but up. And as it goes up, it gets cold. Well, an interesting thing happens to air when it gets cold. It can no longer hold as much water vapor inside. So the water vapor that's from the Indian Ocean, as the air cools and goes up over this barrier of the Himalayas, begins to precipitate. It condenses first out as small ice and water droplets to make clouds, and then continues to condense to form ice, snow, and rain that falls out. As a result, there's an enormous amount of water that falls along the southern end of the Tibetan Plateau, but very little that actually makes it up on to the top of the plateau itself. By the time you get as far north as the Gobi Desert, we understand why this region is so dry now. The air has totally lost its moisture, and there's nothing left to fall there. The Himalayan mountains and the whole plateau, in fact, create a huge barrier for air masses. It also prevents cold Arctic winter winds from coming down into India, keeping India at a very temperate climate around the year. Now, there is liquid water on the plateau, and some of it in very spectacular lakes. Qinghai Lake, also known as Tso Nangpo in Tibetan, is the largest lake in China. The name means the blue sea. That's how large it is. There are numerous lakes that are considered holy to the Tibetan people there, such as Yamdrak Lake, or Yilhin La Lake, and Mapam Yomtso. Namso is one of the most popular lakes for tourism. It's located just 3.5 hours north of Lhasa, the capital of Tibet. The lakes here are just beautiful to visit. Clear, pristine, undisturbed, surrounded by incredibly tall mountains. I mean, there's usually not beach weather conditions here, but it's definitely spectacular to view. There are many places on the plateau that can be very dry. In the Changthan region up in the northwest, temperatures also drop to about minus 40 Fahrenheit in winter. So it is very dry, very cold, and in fact, it's so inhospitable, it has the lowest population density anywhere on the Earth that isn't Antarctica or Greenland. Life has evolved on the Tibetan Plateau in totally unique ways in order to adapt to the extreme cold there. It had long puzzled biologists just how rapidly and efficiently very large hairy mammals had evolved during the recent ice ages. Creatures like the woolly mammoths and woolly rhinoceroses. Well, it turns out they didn't. They had already been eking out an existence up at the top of the Tibetan Plateau. But when global climates turned cold, they came down out of the plateau, finding that they were very well suited for much of the northern hemisphere. It's a theme of this course, repeated over and over, that the powerful forces of erosion are constantly ripping down the land and washing it to the sea. Mountains get eroded faster than anything else. I mean, the Appalachians, again, were once the Himalayas of their day, but after hundreds of millions of years, frankly, there's not much left. So, how is it that the Himalayas are so tall? Well, the simple answer is they're just very young. In fact, they are still going up. They are our best current example of the collision between two continents. You can see this very well if you look at the animation of plate motions that I showed earlier in the course. For example, if you go to a time 200 million years ago, this is when Pangaea still existed as a large supercontinent, you can see that India was nowhere near Asia. In fact, it was landlocked in between Africa, Australia, and Antarctica as part of this giant C-shaped landmass we call Pangaea. If you start to move the clock forward, though, you can see that when the continents broke up, India moved incredibly quickly across into Asia, moving across and closing up the Tethys Sea. By 100 million years ago, it had broken away from Africa with Madagascar, but soon after, it broke away from Madagascar northward and moved towards Asia. By 60 million years ago, it had already started to collide with Asia, and as it continued to move northward, everything that lay in between India and China got smashed up to create this massive plateau that's actually still growing in the current day. What happens in that process is anything that got stuck in between, whether it's ocean seafloor, marine sediments, the existence of volcanic island arcs in the ocean there, even small microcontinents, everything became sort of collateral damage in this collision and got plastered on in between India and China. Eventually, it's no longer possible for the rock to keep going up. I mean, as the collision occurs, the rock has to go somewhere, and the rock gets forced up. At some point, the bottom part of India actually began to slide beneath China. And now we have a situation beneath the southern part of the plateau where you have actually a double layering of continental crust. You have the Chinese continental crust there sitting on top of the Indian continental crust. And that's part of the reason why the continental crust here is so much thicker than normal. Typically, if you look at a piece of the continent anywhere around the world, the average thickness is about 40 kilometers. In the case of the Tibetan Plateau, the thickness is about 80 kilometers. That's just how much rock has been smashed together. It also explains why you can go to the top of these mountains, top of Everest, and you find sedimentary rocks with fossils in them. This rock is limestone. It was once formed at the bottom of the ocean seafloor. The roof of the world is made of rocks that came from the bottom of the sea. Some parts are still rising very quickly. Nanga Parbat, for example, we know is now rising about a centimeter a year. Other parts of the Tibetan Plateau are eroding quickly. But here's an even stranger thing. Some parts of the plateau are actually rising faster than they are eroding because they are eroding. Now, this may sound totally paradoxical, but it makes sense when you look at the process of isostasy. Isostasy is the balance that affects the elevation of the continents. For instance, it's the reason why an ice cube pokes a little bit up above a glass of water. The ice is a little bit lighter than water, so the top of the ice cube sits above the top of the water. Well, the continental rock is a little bit lighter in terms of its density than the rock underneath. So when you smash continents together and you build up a continental, a big continental mountain, you also create a very deep root here. Well, as you start to erode the rock, then the whole continent starts to rise up. For instance, it's like sitting down on the edge of the bed. When you sit on the bed, the whole bed goes down. If you start to get up, the edge of the bed is going to rise up again. So as you remove away the top of the mountain, the whole plate starts to rise up. If you have a few peaks standing high, but you start carving away valleys, as you remove the valleys, the peaks will rise up higher. So it is possible to have your tallest mountains still going up, even while the rest of the mountain range is being eroded away. Now, you can go visit many of these regions, and you can do it the hard way or the easy way. The easy way, for example, is to fly into a city like Kathmandu, the capital of Nepal, and take a variety of tours and trips out from there up into the valleys. Kathmandu is a fascinating city with an ancient history. It's sacred both to Hinduism and Buddhism. But it sits in a very deep valley between mountain ranges, and it's not even a mile above sea level. I mean, it's lower in elevation than Denver, Colorado is. So the temperatures are mild year-round, and the air is easy to breathe. There's also a hard way. You can climb the mountains. These often involve long treks traveling from one base camp to the next, sometimes over many weeks. You need to be in really top physical shape to do this, not only because the height of the ascent and the incredibly low temperatures. Frostbite is very common for people who climb up in these mountains, but because of the thin air. By the time you get to an elevation of 5.5 kilometers above sea level, there's half as much air as there is at sea level. At the top of Everest, which is over 8.8 kilometers above sea level, the air pressure is so low, it's a third of air pressure at sea level. So a person who would normally have to breathe 20 or 30 times a minute would have to breathe 60 to 90 times a minute just to get the same amount of oxygen. Many climbers become physically exhausted simply from the act of breathing so heavily. As a result, people will often take bottled oxygen, and that's become the standard for use in climbing these tall peaks, ever since it was first used in 1922. So when Edmund Hillary and his guide Tenzing Norgay first climbed the summit of Mount Everest in 1953, they had bottles of oxygen with them. However, some of the top climbers today try the ascents without oxygen. In 1978, this was first done by Reinhold Messner, and he climbed Everest without any oxygen at all. 2 years later, in fact, he did it again by himself in just 3 days, from the base camp at 21,000 feet. In fact, some climbers argue against the use of oxygen. They say it lets people up who might not be in top physical shape and have a greater risk of dying. I mean, frankly, a lot of people have died on Mount Everest. On one day in particular, in 1996, there were 34 people climbing Everest, and 8 of them died from the exposure. But as of 2008, Everest had been climbed about 4,100 times by 2,700 different people. The Sherpas there sometimes do it many times. There's one in particular, Apa Sherpa, who's climbed Mount Everest 21 times. And out of those 4,100 climbs, there have been 220 deaths. Because it's often impossible to get the bodies down, the path to Everest is actually lined with the frozen bodies of the people who didn't make it. It is, in any case, a great challenge to reach the mountains, and it's incredibly rewarding. In fact, the difficulty in reaching them actually caused it to take almost 50 years to even determine that Mount Everest was indeed the world's highest mountain. I mean, it's hard to imagine today with satellites and radar. We have laser altimetry, networks of GPS sensors. There's just an incredible technology that allows us to measure our land. Work back then was done by triangulation. You would essentially take known locations and you would measure the angles from 2 points to determine a third and keep working your way upland from the coast. This was first started back in 1808 by the British Great Trigonometrical Survey of India, and they came up with the height finally, almost half a century later, that Everest was the tallest. It wasn't until 1852, in fact. Andrew Waugh, who was in charge of the British survey, redid calculations that had been done over the previous decades, and announced that Everest was indeed the tallest mountain. That announcement didn't come out until 1856. The calculation that he made came out to exactly 29,000 feet. But they didn't want people to think they had rounded off the number, so they arbitrarily added 2 feet to the number and declared Everest as 29,002 feet tall. There have actually been many surveys made since then, both by surveying equipment and by satellite. And though the most common height given for Mount Everest is now 29,029 feet, there's actually still some uncertainty. The numbers vary from about 29,017 to 29,035 feet. So we still don't know exactly how tall Everest is. The Tibetan name for Everest is Jomolungma, which means Holy Mother. But Andrew Waugh named it after Colonel Sir George Everest, who was Waugh's predecessor as chief of the Indian Survey. Now, the Tibetan Plateau and the collision of India into Asia have two other very broad influences. The collision causes tectonic disruption throughout Asia. In fact, most earthquake-related deaths in the world are related to this particular plate collision. If you look at a map of this region, a tectonic map of Asia, you can see that there are faults all over the area. And the deadly Sumatra earthquake of 2004, that was related to this collision. It's the Indian plate colliding into Sumatra. 250,000 people died. In 2005, the deadly Pakistan earthquake happened at the west end of the Tibetan Plateau. That killed 75,000 people. In 2008, on the east end of the Tibetan Plateau, again on a fault that's a result of this collision, 70,000 people died. I mean, this is all India's fault. And the faults propagate throughout Asia, propagating inward, almost like if you took a shovel to snow and you kept shoveling and the snow just built up in front of your shovel. That's what's happened as the Tibetan Plateau has grown outward, and it continues to fault and rupture in the process. There's another very important factor, and that is the role that the Tibetan Plateau plays in cooling the planet, in particular over the past 60 million years. Now, mountains erode very quickly, and there's naturally a small amount of acidity in the atmosphere. In fact, we'll talk about this more later on when we talk about the erosion of landforms. This is in the form of carbonic acid, and it forms when carbon dioxide in the atmosphere combines with water vapor. So the rain that falls out generally is slightly acidic, about a pH of about 5.5. Well, this carbonic acid reacts with rock, dissolves it away, and then ions like bicarbonate ions get washed down rivers and into the sea. More mountains, more exposed rock, more erosion, more removal of carbon from the atmosphere. And that carbon washes down, gets eaten by all the life along the way, plankton, which get eaten by larger things, which end up as the clamshells. Clamshells, after all, are made of calcium carbonate. So that's where that carbon goes. That organic material sinks to the bottom of the seafloor, gets locked away as limestone within the earth. And as a result, the mountains are kind of like sponges that soak up carbon dioxide from the atmosphere. The more mountains you have, the more rapidly you pull carbon dioxide from the atmosphere. Well, why is this important? Well, the carbon dioxide is a critical greenhouse gas that keeps our planet warm. In fact, the time just before the Himalayas, the carbon dioxide levels were about 4 to 8 times what they are now. And as soon as the Himalayas started coming up, the whole world began cooling. In fact, on a very long time scale, our global temperatures have been continuously cooling over the past 65 million years. And a large part of this is due to the rise of the Himalayas. So our current pattern of severe ice ages, that's also partly India's fault. Well, for the top five, let me start first with the Andes in South America. As I already mentioned, the Andes are the longest mountain range in the world. They also have another tall, vast plateau, the Altiplano, which is formed both by tectonic processes and volcanic processes. It's high in elevation, it tends to be very dry, and we'll talk about this more in Lecture 30. Now, the Andes change their appearances as you head from the equator down towards Patagonia. They become increasingly snow-covered and therefore eroded by glaciers as you move south into the southern hemisphere. The Andes began to form a long time ago, at least 1 billion years ago, from multiple plate collisions, some of which we're not even sure what they were. Several of these were continent-continent collisions, like the one that's currently forming the Himalayas. It's often the case that supercontinents like Pangaea will open and close along the same borders. So the same mountain range might have multiple episodes of growth, and that has happened with the Andes. The Andes have also grown continuously over the past few 100 million years with a nearly continuous subduction zone there. So the big Nazca Plate, part of the Pacific Ocean seafloor, has been sinking down here for a very long time, folding, deforming layers of sedimentary rock, taking big wedges of accretionary sediments, the stuff on the seafloor that gets scraped off as these subducting ocean plates sink down back into the mantle. This sediment gets added on as well. And of course, you have volcanoes there as well, adding more rock to the mountains. Next, we go to Alaska for Mount McKinley. Now, I already mentioned that Mount McKinley is the single largest mountain. Simply in terms of its total mass, it dwarfs Everest in comparison when you put it side by side. Everest has the advantage that it's already starting out on top of a huge Tibetan plateau. Mount McKinley is part of its own long mountain range, the Alaska Mountain Range, which goes for about 1,000 kilometers. Next, let's go to the Rocky Mountains in North America. We saw this 2 lectures ago in the Burgess Shale, and the Rockies extend a great distance, both in the United States and up into Canada. It's about 3,000 kilometers long, begins in New Mexico, and ends up in British Columbia. In the United States, the Rockies formed 80 to 35 million years ago. It's a mountain building event we call the Laramide orogeny. Orogeny means a mountain building. And as I mentioned before, this is largely due to North America going over the ancient Farallon Pacific Ocean seafloor, and that young, buoyant slab pushed up North America and forced up the Rocky Mountains. It actually has a very complex geology. The mountain building of the Rockies happened in fits and starts over various periods. Last, let's go to Europe for the Alps, which are the major mountain range of Europe. And actually, I should say that all of those mountains, the Alps, are directly related to the Himalayas in a way. They are all part of a long mountain chain that's all associated with the close-up of that ancient Tethys Sea that followed the breakup of Pangaea that started 200 million years ago. This includes the Alps. As you go into Eastern Europe, the Carpathians and the Caucasus and the Zagros and the Hindu Kush and Pamir and Karakoram and Himalayas. If you look at a map of the topography of Eurasia, you'll see this long ridge that connects all of these all the way across. The tallest peak in the Alps is on the border of Italy and France. It's Mont Blanc. It's 4.8 kilometers above sea level. Though perhaps the best known geologic feature of the Alps is the Matterhorn, which is along the border of Italy and Switzerland. It comes to a very sharp peak that has been eroded by glaciers carving away all sides of it, leaving a stunning point, and it's a very striking landmark. Well, In this lecture, we've seen some of the geologic wonders of the giant Tibetan Plateau. In the next lecture, we're going to see what happens to all of that rock when it gets eroded away, and we're going to visit the Ganges River Delta.